Assalamualaikum warahmatullahi wabarakatuh. Let me introduce. My name is Bittang Mikhael, and I'm currently studying in Universitas Pembangunan Nasional Veteran Yogyakarta, and I'm one of the student of Teknik Kimia with the student ID number 12 12 30 206, and I'm deeply passionate about the world of science, especially in the field of biotechnology technology and biochemistry. Throughout my academic journey, I'm developing a particular interest in studying understanding complex biological systems, the innovative methods that drive advancements in the biotechnology. One area that I find particularly fascinating is the engineering of antibodies. This involves both experimental and computational method that helps in development antibodies for therapeutic purpose. So today I'm going to present about about affinity about a journal that I review, and it's about affinity maturing of antibody fragments. A review encompassing the development from random approach to a computational rational optimization, and it's a field with vast implications for treating disease. My interest in this area was sparked during my research on the measurement of sugar using refractometry, which I studied earlier this year. This explorating into scientific instruments and their applications opened my eyes to the importance of precise measurement techniques in a chemical, physical analysis and pharmaceutical research. I'm motivated. I'm motivated. I'm motivated by the potential of combining laboratory techniques with computational tools to solve real-world problems, particularly in biotechnologies. Throughout my studies, I am honing skills that will allow me to contribute to the growing field of drug development, bioengineering, and molecular research. Looking forward, I hope to continue expanding my knowledge, conducting research, and ultimately contributing to groundbreaking advancements in science. In addition to my academic interests, and I'm always excited to collaborate with like-minded individuals and share ideas about how we can make a positive impact on the world using science and technologies, and I'm eager to continue exploring new avenues in my studies and future career, and look forward to what lies ahead in the fascinating field. So, back to our presentations that I'm going to about talking about top, that I'm going to review is the uh, affinities measuring of antibody fragments. So the journal that I review is about affinity maturations of antibody fragments. It's a review patients the development from random approach to computational rational optimizations. And the writer for this journal is Jia Jiayi Li, Wang Bokang, Chia-Wen Wang, Haibin Yuan, Yili Wu, Xiaoxian Meng, Ping Wang, Miao Xiang, Yuli Wang, Yonghang Feng, He Huang, Ario De Marco. And the journal name is about the International Journal of Biological Macromolecules, and the release of this journal it received on 3rd April 2023 and received in revised form 4 July 2023, and it's accepted on 6 July 2023, and it's available online on 7 July 2023. And the routinely and first I'm going to talk about the journal, and it's routinely screened antibody fragments usually require further in vitro maturation to receive the desired biophysical properties. Blind in vitro strategies can produce improved ligand lic- improve ligands by introducing random mutational into the original sequence and selecting the resulting clones under more and more stringent conditions. And rational approach exploit an alternative perspective that aims first and at identifying the specific residues potentially involved in the control of biophysical mechanisms, such as affinity or stability, and then to evaluate what mutational could improve those characteristics. The understanding of the antigen and antibody interaction is instrumental to develop this process, the reliability of which consequence strongly depends on the quality and complementness of the structure's information. Recently, method based on deep learning approach critically improve the speed and accuracy of model building and are promising tools for accelerating the docking steps. Here we review the features of available bioinformatic instruments and analyze the report illustrating the result obtained with their application to optimize antibody fragments and nanobodies in particular. Finally, emerging trends and open questions are summarized. Okay. More than 30 years have been passed since the United States Food Drug Administration's FDA approved the first monoclonal antibody in 1986. In the period, antibody engineering has become progressively simpler due to introductions of more precise and versatile techniques of gene manipulating. This technique progress allowed the development of a large number of biotherapeutics based on monoclonal antibodies that have been effectively humanized and produced in multivalent and multifunctional format. Multivalent constructs can exploit AVD to compensate for low affinity that for therapeutic drug development should be lower than 1 nm. Multispecific constructs provide even more selective binder by combining ligands specific for independent epitopes. In the perspective of constructs combining more ligands, recombinant antibody fragments offer clear advantage over convention IgGs MABs because their short sequence can be engineered with basic genetic techniques to improve the contract biophysics and functional feature, and their derivatization is simple and reprodu- reproducible. Furthermore, Their physical dimension remains limited also when polymers are constructed there. They have low production costs and at least when nanobodies are used have reduced immunogenicity. The circulation's half-life of recombinant antibodies can be tuned by varying the overall dimensions and or promoting the binding to albumin and IgGs. At least in the case of nanobodies, there is the options to choose between libraries obtained from immunized animal and pre-immune libraries. Naive or synthetic, the first option exploits the in vivo somatic maturation to recover clones with increased affinity, and specifically for particle antigen, where pre-immune libraries can be challenged against any antigen and have advantage to meet the expectations of the regulative authorities that especially in the European Union and synthesize protocols that avoid the exploitations of lab animals and spare their life. The quality of a pre-immuned library depends on several features, but it accepts that large functional diversity facilitates the identification of better binders. Consequently, the DOP display system might significantly contribute to the possibility of identifying effective binder because it determines the library theoretical dimension as well as the planning efficiency. In the most of the case, the process of sections starting from antibody fragment pre-immunite collections result in the isolations of clones that are concentrate hits and require further in vitro maturations to receive the desired biophysical characteristics. These procedures that comprise an extensive quality control steps is laborious and time-consuming but necessary to reach reagents with standards suitable for therapeutic application. If affinity is a key factor for antibody evaluations, productivity, low aggregation propensity and stability are other critical elements to consider to optimize the overall antibody development, and this implies the necessity to try optimizing all these features. The major issue of this step is the improve of different biophysical parameters of often require conflict actions, namely the optimizing optimizations of a parameter can induce the negative effect on other. From this point of view, nanobodies provide being particularly valid candidates of optimizations because their often highly initial stability can be better than structural modification introduced to improve other features such as affinity. Various in vitro strategies have been developed to identify improved candidates inside a pool of mutants of the initial hit. This blind approach they rely on the empirical capacity to select clones which increase biophysical characteristics by adapting progressively. By more stringent conditions during the screening of the mutants libraries. By applying such as procedures, it is impossible, for instance, in selecting clones with higher affinity with respect to the original binder, but still maintaining the structural stability that enables correct display as soluble molecules on the face surface. The drawback of the method is that it does not explain the rationale that provides the improvement characteristic. Alternative approach exploit the strategy based on sequence compression to identify key residues potentially involved in stability and aggression. Finally, structural models and the analysis of their biophysical parameters can be used to design binders from both initial hits or totally ex novo, and introduce specifically variants. The advantage of using antibody fragments, such as nanobodies, is present by their short sequence that requires less computational efforts for any kind of analysis with respect to large molecules such as IgS. In recent years, computer-assisted in silico affinity maturing technologies has critical progress taking advantage of the rapid development of protein structure-based, rationally designed algorithm optimizing and higher computing power availability in parallel, or our overall knowledge of antibody antigen complex structure has grown. Different strategies for antibody fragment rationally designed have been developed, which includes homology modeling, molecular dynamic simulation, molecular docking, mutation hotspot design, and interface residues analysis. Altogether, computer-assisted antibody fragments rational design is maturing into an effective tool for the optimization for their biophysical properties, such as affinity, specificity, and stability, both in vitro and in silico optimization. Approach applied to SCFVC nanobodies have been described and commented, but the analysis remain confined to specific topics and applications. At the same time, this research field evolves very rapidly and updates required to be integrated to provide a complete picture. In this review, we have summarized the potential and the challenge of the different available approach by comparing the method used to measure recombinant ligands in vitro and in silico, and to predict antibody-antigen intersections. Measured technologies have been mentioned, verified, and illustrated by few reference phase. More attention was dedicated to fast development research field to outline emerging trends and applications. Okay, now let's move on to the topics that I'm going to talk about. And here's the things I'm going to talk about: the review of the journals that I found or took. So, first, we're talking about the background. Second is research objectives. Third is research methods. Fourth is result and discussions. Five is conclusions, and six advantage, and seven is disadvantage. Move on. So, antibodies are crucial in diagnosis and therapeutics. Over years, their engineering has advantage from traditional methods like random mutagenesis to sophisticated computational and techniques. Antibody fragments are smaller portions of antibodies such as single-chain variable fragments (SCVs) and nanobodies. These fragments are easier to produce, less expensive, and offer specific advantages like reduced immunogenicity and better tissue penetrations. To be therapeutically viable, Antibody fragments often need affinity maturation process to enhance their binding strength, stability, and other biophysical properties. With advanced like learnings, computational tools now allow faster and more precise optimizations of antibodies. And the research objects are first, and the research objects of these review journals of in the journals they study aims to compare traditional in vitro laboratory based and in silico computer based method for optimizing antibody fragments. Second, it focuses on how computational tools including machine learning and deep learning and can be replaced or complement traditional methods. And third, is the goal is to highlight trend challenge and optimize potential potential of these technologies technology these techniques in making antibody optimizations more efficient and scalable. Okay, moving on the research methods. In vitro approach, these experiment techniques conducted in a laboratory settings, and the goal is to introduce change into the antibody fragments and test them for improved binding strength, stability, or other properties capitalized. And in humoral immunity, somatic maturation is responsible for the progressive affinity increase of antibodies towards antigens. In vitro maturation tries to reproduce such as mutagenesis process by introducing more or less control mutations in the original sequence. The resulting mutant libraries are then screened using conditional select to favor the isolations of clones with improved characteristics such as binding capacity or structural stability. The process does not require any preliminary knowledge about structures and antigen antibodies complex chara- characteristic has proved being effective in several cases and can be implemented adopting alternative mutagenesis strategies. Given the random nature of the approach, in vitro mutagenesis can introduce sequence liabilities that can affect the antibody developability, and this issue must be acknowledged and addressed. And point mutations randomly altered specific amino acids in the antibody sequence. Mutations are often target to the regions most involved in binding, like the complement determining region or CDRs. The limitations can be time consuming as it requires screening many variants. On the point mutations, the point mutation approach aims at introducing random mutations of few amino acids in each newly generated clone corresponding to the initial target sequence. The effective the effective mutation rate should be sufficient to provide structural alternative but not too high to avoid complex analysis of clone in which mutation introduce positive and negative effect might compensate. Mutations are often limited to the CDRS because this sequence contributes to most of the paratopies. rather than be induced randomly along the whole antibody sequence, with the risk of challenging the molecular stability. However, mutation of the frameworks can be beneficial, as demonstrated experimentally by progressively introducing random point mutation in both the VH and VL domains. A CVF increase its affinity for estradiol 17 almost 250-fold with respect to the parental fate, to a final Kd of 1.3 x 10 minus 10. The affinity by the cam- camelized murine antibody AFB Lin increased more than 20 times by combining points mutations in FR2, FR4, and CDR3. The CDR3 domains in the major target of random mutagenesis for VH domains, and despite its usually long sequence, this strategy still reduces drastically the number of potential variants and the downstream characterizations workload. There is a general trend to the address preferentially binding hotspot with the mutagenesis, and the computational method result useful in their identification. On DNA shuffling cuts antibody DNA into smaller fragments and recombine them randomly to generate diversity. This method is effective for creating large libraries of potential variants, for example, used to improve the stability and affinity of llama single-domain antibodies. The DNA shuffling. This technique requires the generation of random DNA fragment libraries of select sequence portions that are then reassembled into full-length sequence. It can be used with longer DNA sequence than point mutation approach based on error-prone PCR. Harms and ETAL employment DNA scuffing to improve the characteristic of a llama single-domain antibody fragment, obtaining a mutant with increased stability threefold and affinity tenfold. The same method enables the recovery of a SCFB mutant against SARS-CoV with the equilibrium dissociation constant 270-fold lower than the original clone, and to improve significantly the affinity of an EGM antibody against pro-castrin-releasing peptide strategy extension process STEP is the mutagenesis option based on repeat cycles of the implant denaturation and very short analysis polymerase catalase extension step that has been used for promoting protein evolution, although not commonly exploited for recombinating antibody affinity maturation in combination with chain shuffling. It provides being suitable for such applications by introducing mutations spanning uniformly throughout the length of antibody construct in an unbiased way. The approach allows both inter and intra-chain recombinations and simultaneous mutation in all CDRs, generating variants that will screen by ribosome display. Recently, the potential of nucleotide insert and delete indicus to expand the antibody diversity during somatic hypermutations has been described, and it successfully applied in to the in vitro affinity maturation of some antibodies in parallel. An autoaggressive generative model has been envisaged to evaluate indel effect on nanobody variant performance. Moving on chain shuffling, it replaces one chain of antibodies, either heavy or light chain, while keeping the other constant. This method is particularly useful for identifying better complementary chain pairing. The chain shuffling is a method used for diversification of recombinant binder originate from conventional antibodies. In the approach, one of the antibody chain is replaced by a repertoire while the other chain is kept constant. The chain shuffling has been used to generate high affinity antibodies starting from genetic materials obtained from immunized animals, and has been applied to both SCFBS and FABs chains. Shuffling allows insulating SCFB monotanes with 58-fold higher binding affinity to organize 2 and monovalent antigen binding fragment mutant specific for copratoxin with affinity 8-fold higher than the original clone. Moving on to the next slide. There is CDR walking. Introduce mutation one CDR at a time. After optimizing one region, the best antibody is used as the starting point to optimize the other region. Examples successfully increase the affinity of antibodies in stepwise manner. The CDR walking exploit an interactive to introduce variants exclusive in the CDR regions. Generally in different sub-libraries are prepared and mixed before undergoing panning to identify improvement mutants. Next, the best antibody resulting from the maturing of one CDR is used as the reference for the optimizations of the other CDRs. The, modifi- the modification of CDR-H1 and the CDR-H2 after preliminary steps of CDR-H3 saturation's mutagenesis result in the 167-fold affinity improvement with respect to the parental BAK1 antibody. The approach is faster and more efficient when optimizing its performance in burial on both SCFP lumens till et al. Conduct simultaneous CDR-L3 and CDR-H2 diversification using three nucleotide consequent casetes followed by domain combination to obtain a mutant with 5,000-fold improvement affinity. The same strategy was successfully increased 420-fold the affinity of FAB before or 12 for the HIV in one envelope protein GP 120. Last one is naturation's mutagenesis. Mutates all amino acids in a specific regions, typically where there is prior evidence of involvement in binding, and limitation is generates many variants, making downstream screening challenging without computational tools. The Saturn's metagenesis is a semi-rational approach that foresees the mutation of all amino acids in a short region of gene. Commonly used saturational mutagenesis techniques include cassette mutagenesis, PCR amplifications, gene splicing by overload extensions, and mutagenetic plasma amplification. It can be considered an extension of a point mutation approach used when there are indications about potential target amino acids, since the information might be on no sufficient precise. The method can provide very deceiving results. It is suitable for a single loci because when it is applied to more loci contemporaneously, the number of possible sequences increase exponentially, making difficult performing the experiment downstream analysis. This drawback can be reduced by exploiting bioinformatics tools to remove clearly defective clones from mutant libraries. Site saturation mutagenesis of a protease-sensitive sequence was successful in reducing the proteolytic pro- propensity of MMP14 inhibitory antibody, and is increasing tenfold the affinity of nanobody directed against Clostridium at difficile dosing A. Okay, moving on. Okay, now it's in silico approaches. This computational method simulates mutations and predict outcomes without physics experimentations. These techniques leverage advanced algorithms, structural database, and machine learning. First of all, homology modeling. It's built 3D models of antibodies based on known structures of similar antibodies and relies on conserved sequence and structural features to predict the most likely shapes. And second is molecular dockings. It simulates of how an antibody binds to its antigens by analyzing the interactions between their structures, determine which mutations improve binding based on energies and compatibilities. And third is deep learning and AI based model. It uses large data sets of antibodies, antigens, interactions to train neural networks. Tools like AlphaFold and NanoNet predict antibody structures and evaluate mutations rapidly. Its benefits can handle highly complex interaction that traditional methods struggles with. So, affinity measuring by rationals in silico-based approach, despite in vitro methods were demonstrated to be effective, they are extremely time-consuming, and it cannot be expected that this bottleneck will change significantly in the future. Reportedly, the number of and clearly shows that in silico methods are becoming popular. In recent years, computer aided method been have been applied to antibody research and drug discovery for improving affinity, specificity, their most stability, humanizations, and limiting aggregations propensity. Example of difference in silico affinity measuring software software applies to antibody fragment are reportedly in such rational approach rely on algorithms, the effects of which progressively improve and on constantly increase of computational capacities. It means that in silico methods will be more and more reliable, rapid, and precise, even though at the present they are not always more effective than wet lab, optimizing option in terms of required times and outcomes. Conventional proteins rational design method usually refers to thermodynamic principles and try to identify the conformations with approaches. X-ray crystal crystallography has been the standard method for dissecting an interaction between antigens and antibodies, but need to be fully solved. NMR NMR is difficult to apply to decipher complex protein structures because of their large mass, but can be exploited to identify antibody residues contributing to build contact surface when it is the case of nanobodies. The dimensions of the ligands is small enough to be compatible with the technology. Cry, Crime represent the newest options to study antigens-antibody interactions, and its increased value of such technologies is boosting the process of protein and proteins complex structure resolutions. Furthermore, hydrogen deuterium exchange mass spectrometry HDX MS is an effective method to identify the reduced involvement in the epitope paratope interaction surface, as other technologies require both expensive equipment and specific expertise. HDX-MS approach is still confined in a relatively restricted number of labs, but it provides being extremely successful to study the interactions of protein with both small molecules and other proteins, such as in case of antigens antibodies complex, and demonstrate being particularly useful for the identification of conformational epitopes as they are recognized by nanobodies binding to junctional epitopes, and to discriminate the antigen sites that induce the different neutralization response. ADX-MS has the advantage of being measurement in solution, thus preventing artifacts due to crystallizations or freezing, and allows the study of complex systems such as membrane protein and protein aggregates. Its main limitations is that it does not provide information about which antibody residue interact with which antigen residue. As a compared to crystallography or CRO-AM, therefore similarly to the procedure applied when an epitope mapping is performed with NMR HDX MS, data should be combined with docking experiments to refine the binding model and identify the residues that are rearranged exclusively because long-distance allosteric conformation change as an alternative to experiment method computational-based structures predictions. Method has demonstrated as astonishing of level reliability for constructing automatic resolution models of target proteins starting from their amino acid sequence. Some of them are suitable for any protein class and others specifically designed for dealing with antibodies. A template-based approach, comparative homology modeling and treat methods. These protein structures predicts methods including homology modeling and treating methods rely on detectable similarity between target sequence and known structures in the case of conventional antibodies. Homology modeling exploit the characteristic of conserved antibody sequence corresponding to framework and CDRs, determined by applying the standardized numbering method COTIA and UPNUM. The framework sequences are highly homologous and easy to model, while the CDR loops are highly variable and requires additional constraints for accurate modeling. The greatest challenge is predict the conformation of CDRH3, which is the most variable in length and sequence and usually contribute mostly to part, uh, parot bed formations. Uh, okay. PIX Pro and Rosette antibody are typically used for modeling approach, whereas the evaluation of nanobodies thermodynamic characters is significantly supplied by the low residue number of such ligands, and the advantage vanishes when nanobites must be modeled. This is because there are relatively few available structures with respect to conventional antibodies, and their information significant deviation from the from that of from that H VH, a domain with shorter CDR3 sequence and display affected by the co-presence of light chain loops. Consequently, the main challenge is to adapt platform design for VH domain of conventional antibodies to the specific structure characteristic of VHHs. Modify prosthetic antibodies for nanobites has been dismissed, where the antibody structure were the prediction algorithm a bodybuilder in combination with the structural antibody database SABDAB was successfully tested to model nanobodies despite the promising characteristic and the confirmations of its capacity to predict antibody 3D structures. A bodybuilder has not been used frequently, and its comparative work exhibits less accuracy in modeling the H3 loop and the Rossi TTA fault and Swiss model. Modular and Swiss model are still the most common software used for nanobody modeling. Specifically, Modelly is an easy-to-use homology modeling software that is very effective when suitable homologies tabled with high similarity and coverage can be retrieved from the protein database. It was exploited to obtain structural model nanobody specific for several antigens such as VGR2, TN, TNFR1, PLA2, MMPA, DARC, and BMP4, and various toxins. Treatment methods were developed to recognize proteins with low sequence homology but similarly fold and operate matching the query sequence directly onto the 3D structures of solved protein. Decompositions the template structures into local structure features and iteratively updated sequence profiles of multi-sequence alleles to identify distantly homologous templates. This approach has been applied by different platforms such as GenTrader, Orion, Findsite, E-Taser, and GenTrader is suitable when the target is relatively complex and its flexibility and dynamics need to be considered. Orion's aim to identify local structure informations, protein blocks corresponding to pattern that can be accurately describe protein models and predict the structure global rather than membrane protein. Findsight is useful when the target sequence is not very similar to the template, but the two share some conserved regions. One e-taser can be applied to combine the result of various structures, break the tools, and improve the accuracy of the final model. The trading-based serve Raptor X succeed in modeling VHHs against different toxins, and E-Taser web server was used to model the structure of VHHs against the HCV non-structural proteins NS3-4A and protein A. E-Taser maximized contact map prediction and optimized one E-Taser force field which can be handled structural region lacking accurate spatial restraint. Early methods present rely excessively on the manual setting of scoring parameters and their search phase were relatively fixed. Currently, they all provide easy-to-use web server for simple submission and result recovery and have integrated deep learning models that overcomes the limitation of standardized manual settings. The implementations of automatic parameter and method integration for target maturations allow carrying out deep sampling and search in global confirmation space. Two factors that contribute tracing optimized by avoiding to be trapped into local optimal solution. This approach allows to obtain model as accurate as those built by traditional homologous method even when structural data are particularly scarce. Okay, next. So the result is that the in vitro methods for antibody affinity maturations such as random mutagenesis, point mutations, DNA shuffling has been shown to be effective in generating high affinity antibodies. These techniques involving introducing mutations into antibody sequence and screening large libraries of variants to identify those with improved properties. For example, point mutations in completely complementary determined regions (CDRs) have led to significant increase in affinity, with some antibodies showing up to 250-fold improvement in binding strength. DNA shuffling and chain shuffling are also used to create defined libraries, providing the opportunity to improve stability and affinity across various antibody fragments. However, in vitro methods are labor-intensive and time-consuming, requires multiple rounds of mutations and screening. While these methods are effective for minimizing binding affinity, they are often result in trade-offs such as decreased stability of or resolvability, which complicates the optimization of multiple properties simultaneously. In contrast, in silico methods, including molecular dockings, homology modeling, and deep learning, offer faster and more precise alternatives. Computational tools such as AlphaFold and Nano have apply research and predict 3D structures of antibodies and their interactions with antigens, allowing for Rabbite simulations of mutation and their effects. These methods have proven to be highly effective in identifying key resides involving in antibody-antigen interactions, enabling research to provide mutations that will enhance binding affinity. Despite this advantage, in silico methods still face challenges, especially in predicting complex traits like antibody stability, solubility, and aggregation propensity, all of which are critical for their therapeutic application of antibodies. Moreover, the accuracy of in silic predictions depends heavily on the quality and diversity of the data used to train the models. The discussions, mm, wait, the discussion, the in silico approach, particularly those based on deep learning, have significant and change the speed and precisions of antibody affinity maturizations. Tools like AlphaFold have revolutionized the field by providing accurate structural prediction for antibodies, allowing the research to quickly identify key regions for mutations, optimize interaction with antigens. Deep learning models such as NanoNet have demonstrated considerable success in modeling the unique structures for nanobodies, a class of antibodies fragments with distinct properties. These models have enabled research to simulate millions of potential mutations, drastically reducing the time and resource required for experiment validations. However, despite their effectiveness, in silico methods are not without limitation. While these tools are accurately predict binding affinity, they still struggle to model more complex biophysical properties like stability, solubility. Optimizing one property such as binding affinity often comes at the cost of others, like stability of aggregations, making it difficult to improvise multiple characteristics simultaneously. Furthermore, the success of computational tools slightly depends on the quality of input data. If the structured data of the antibody's antigen complex is limited or biased, the accuracy of the predictions can be compromised. To overcome these limitations, a hybrid approach that combines in vitro and in silico methods is emerging as the most effective strategy. In the approach, computational tools can be used to predict and prioritize mutations which are then experimentally validation. This combination allows research to refine their models based on real-world data, optimizing both the speed and accuracy of the affinity maturation process. Additionally, the development of new computational tools for prediction development of antibodies such as SMC, MAB, and Deep DDG is promising. These tools allow research to predict how mutation affects an antibody's stability and folding, helping to streamline the development of antibody suitable for therapeutic use. As computation techniques continue to evolve, they are extended to play an extremely important role in a field of antibody engineering, potentially accelerating the development of more effective and prescient antibody based on therapeutics. Okay, okay, moving on conclusion. The conclusion underscores the balance between traditional laboratory based methods in vitro and the newer computational techniques in silico in the optimize of antibody fragments. The integration of these two approaches promising to overcome the limitation of each, particularly in terms of time, cost, and the complexity. Optimizing multiple biophysical properties of antibodies simultaneously, while in vitro methods can be produce high affinity antibodies, their time consuming nature makes them less scalable in silico approach. However, excellent speed and precision but need more advancement in prediction broader biophysical characters such as stability and solubility. Combining both methods creates more robust pipelines for development therapeutic antibodies. The progress in computational tools like AlphaFold and NanoNet highly the increased reliance on computational methods in modern biotechnology. As this tool improve and new ones emerge, researchers are likely to see even greater efficiency in antibody design. The future of antibody engineering lies in harnessing the strengths of both in vitro and its silico approach, making the entire approach from design to therapeutic application more streamlined and accessible. Okay, moving on to the disadvantage and the advantage. In advantage in vitro methods, this directly generate antibodies and test them in real biological environment, ensuring that the results are based on actual biological behavior. Random mutagenesis and other traditional methods has been successfully used to improve the affinity to antibody fragment for over 30 years, making them reliable choice for many applications. And in vitro methods do not rely on a data or pre-existing knowledge about the antibody-antigen interaction. They are flexible and that can be applied even when limited structural data is available. This method can introduce a wide variety of mutations such as point mutation, shuffling, or saturation mutagenesis to optimize different antibody properties simultaneously. On the other hand, on disadvantage, in vitro methods are highly labor intense and time consuming. They are require multiple rounds of mutagenesis and screening, making the process slow and reduce heavy scaling up to process to test thousands of variants in is difficult and constantly, especially when working with complex antibody libraries. Optimizing one property often leads to the creations of another. This makes it challenging to optimize multiple properties simultaneously. This method requires significant materials research and specialty expertise, making them more costly compared to computational approach. Okay, moving on in silico's methods. The advantage on this, especially those powered by deep learning, can predict antibody structure and optimize mutation much faster than traditional methods. This reduces the time required for experimentation. Computational methods save on material costs since they rely on accessing data and simulations rather than laboratory reagents and resource. These tools can predict specific mutations that are most likely to improve affinity, stability, and specifically based on the 3D structures of antibodies and antigens. This reduces the needs of broad random screening. Computation tools can evaluate thousands of mutation quick, making it easier to scale the optimizing process without significant increase in cost or time. In silico methods can analyze interactions at the atomic level, providing insight into the fine details of antibodies antigens binding, which may be difficult to capture through in vitro methods alone. On this advantage, the accuracy of in silico prediction is heavily depends on the quality and quantity of available data. Poor or insignificant data leads to inaccurate model or predict reducing the effectiveness of the method. In silico method are the best suited for optimizing antibodies with non-structured previously studied interaction for novel or poorly understand systems. The lack of data may limit their effectiveness, which this tool accurately predict binding affinity, predicts more complex biophysical traits such as antibody solubility, aggregations, and overall development remain a challenge. Advanced computation tools, particularly those based on deep learning, require significant computation power and infrastructure which may not be readily available to all research. And thank you. That's all from me. Assalamualaikum warahmatullahi wabarakatuh.